Hey everyone, welcome to our next section going through molecular compounds. We've covered ionic and polyatomic so far, and you've had a little bit of time to practice as well. And so just as a little warm-up, I'd encourage you to kind of read through the question and see if you can't come up with answers for each one. So pause the video, take a look, and come back when you're ready. Alright, so number one says, how can you tell which of the following is the ionic compound and which is polyatomic, and then to write the symbols for each one. So, if we were to take a look at our first one, we've got aluminum carbonate, and so aluminum, it says, how can you tell which of the following is the ionic and which is the polyatomic? And so we need to take a look. Aluminum and potassium aren't really going to tell me much because they're just the metal groups that are there. But if I take a look between carbonate and chloride, that should give me a pretty good indication as to which one is the ionic and which one is the polyatomic. So by taking a look at carbonate, I can see that carbonate, if I look at my periodic table up on the top, is CO3. And so carbonate is going to be my polyatomic group. Whereas if I take a look at chloride, chloride's just on the periodic table itself. And so chloride is just going to be a regular ionic compound. Now, realistically, both of them are ionic compounds because they both involve metals and groups of nonmetals. This one can also be referred to as monoatomic, which just means singular, whereas the other one is poly, which is many. And so we're just separating them just based really on monoatomic and polyatomic, but they're both ionic compounds in general. We just refer to one just as its base unit as ionic compounds, and the other one is polyatomic. So after that, to write the symbols out for each one. So if I have to write out the formula for this, aluminum has a 3+ charge. And then if I take a look and I find carbonate on the table, it has a 2- charge with it. If I take a look for potassium on the table, potassium has a 1+ charge. And if I take a look for chloride, it has a 1- charge. And so now that I have the charges, I need the symbols, Al and CO3. And then carbonate has a 2- charge. Aluminum has a 3+ charge. I'm going to give myself just a little bit more space here so I can write in what the numbers are going to be. Remember, we crossed the charges and dropped the signs, so carbonate's going to cross with the 2, and then aluminum's going to cross with the 3. Between the 2 and the 3, I cannot reduce it any further, so I'm done there. In potassium chloride, each one has a +1 -1 charge, so when you cross, they're just ones. So this is just KCl. In the next part, how can you tell which of the following is the ionic compound and which is the polyatomic? And so again, if I look at the metals, they're not going to help me very much. I need to look at the nonmetal groupings, and so here I have a group of nonmetals with NO3, so this one is going to be my polyatomic group, and this one is going to be my regular monoatomic or ionic group. And so saying the names for them after that, write the names for each one. This one is just going to be sodium and then oxide, and the only time I would use Roman numerals here is if I have a element that can have more than one charge, and those typically are found in your transition metal areas. In the next one, I've got beryllium, and so beryllium, and I have to find NO3 on my table, and NO3 is nitrate, and so remember, we don't change the endings that are there. So for polyatomics, the endings stay the way they are, and for ionic compounds, we change that IDE from oxygen to oxide. So that kind of recaps our monoatomic and polyatomic, our ionic compound groupings, which really lets us start to move ahead into molecular compounds. So in terms of molecular compounds, most of the compounds that you encounter every day actually don't contain any ions at all. Rather, they're neutral groups of atoms called molecules. So things like sugar, things like water, things like carbon dioxide, they're all different examples of molecular compounds. So, What are molecular compounds? They're made up of just nonmetals that share electrons to become stable. There are some exceptions with group 2 and group 13 metals that can form weak molecular bonds, but the vast majority of them are nonmetal groups that share electrons to become stable. So if you took a look at page 201 and figure 1 in the textbook, that also gives you a little bit of an idea just kind of what molecular compounds are. So the bonds that are between ionic compounds, they tend to be made up of ions of opposite charges, but here, however, with molecular compounds, they're made up of neutral charges. And how do they kind of get there? So ionic charges, I take a look at this kind of +1, -1, or +2, -2 scenario where things are gaining or losing electrons. With molecular compounds, I have to think of overall what do these elements need. And so a lot of the time they want to share their electrons to fill their valence shells, so to fill their outside shells to make sure everything is balanced. So I'll make this a little bit smaller so we can see. So covalent bonds, the bonds in molecules, they're called covalent bonds. Before, what would happen with ions is that they'd essentially be taken and they would end up sticking around in like a lattice structure. So they would stay with these positive and negative charges. In molecular compounds, however, the electrons are actually shared between elements, and so when I have a shared pair of electrons, we get these guys called covalent bonds. So a covalent bond, the shared pair of electrons between atoms in such a way that it fills the outer shell of the atom. And just noticed does not have an E. That is, it fills the valence electrons for that shell. So some examples that are here, let's take hydrogen for instance. Hydrogen wants to have 2 electrons in its outside shell in order to be stable. So if I were to take my hydrogen atoms that are here and I were to turn them to their sides, then we can kind of see how these things would end up overlapping, where I have this overlapping ring that covers 2 electrons for each one. So it's like each one is donating an electron and sharing it with the other one in order to have a full shell. So many nonmetallic elements, they exist as covalently bonded molecules. They're called diatomic elements, and we can see table 1 in your book, which is page 202, to take a look at these diatomic elements. So really there's 7 of them in general when we start to talk about diatomics that exist kind of in groups of 2. And those 7, if we were to take a look starting from our halogen group at iodine, those 7 tend to make a 7 starting from iodine. So we do iodine, bromine, chlorine, fluorine, oxygen, nitrogen. So that kind of makes a 7 on that table, but then we also add in hydrogen as our last one. So there are 7 diatomic molecules. All that means is that when they exist in nature, they exist in groups of 2. So if I were to find oxygen, for instance, we breathe in oxygen. We don't just breathe in one atom of oxygen at a time. We actually breathe in oxygen gas, which is O2. So all of these elements, when they exist in nature, actually exist as pairs of elements, and so they exist in groups of 2. They're called diatomic elements, or diatomic molecules. So whenever we see questions that start to talk about oxygen gas or hydrogen gas, we have to keep in mind that those are in groups of 2. These covalent bonds, they can also form together to make molecular compounds. So let's take a look and see, just like our hydrogen, let's take a look at a couple different examples here. So on the left is a Bohr model that ends up talking about carbon, and we can see that carbon has 2 electrons in its first shell. That makes sense. And then its outside shell has to have 8. Well, carbon only has 4 other electrons in its outside shell. It had 4 valence electrons. But there are 4 hydrogens that also want to overlap to fill their outside shell, which only needs 2. So when carbon is satisfied, it has 8 electrons in its outside ring. Okay, if we were to follow them through here, right, 8 electrons in its outside shell going through carbon. But then each hydrogen is also getting a benefit because each hydrogen is picking up 2 electrons, and that's what hydrogen needs to be stable as well. So Molecular compounds use covalent bonds, use these ideas of sharing electrons to maximize the strength of their individual elements by fulfilling their shells. I can take a look with water. It's the same thing. We have an oxygen atom in the middle, and so oxygen has 2 electrons in that first shell, and normally it has 6 outside of that. And so each hydrogen atom is then sharing its extra electron with oxygen, giving oxygen a full 8 around its outside shell, so it's stable. And then also hydrogen gets a benefit because it also gets an extra electron from oxygen, and it becomes stable. So hydrogen has 2 electrons in its outside shell, and oxygen would have its full valence shell at 8 electrons. So there's a whole thing with naming molecular compounds. Similar to ionic and polyatomic, we're going to focus our attention just kind of on naming and drawing to make sure that we gain an understanding of how it works. So there's many common names for molecular compounds that don't follow any rules at all. We have things like common names like water, H2O. We have ammonia, or NH3. We've got methane, which can be CH4. We've got hydrogen peroxide, H2O2. And there's a list of a few of them that are there. So these ones are common names. It's not to say that if we didn't name them, like I'm going to show you here, that they're wrong, but these common names are, widely known to represent those molecules. So otherwise, when we name them, prefixes are also used to indicate the number of each element in the molecule. And what I'm going to show you is that they're called IUPAC naming systems. It's the International Union of Pure and Applied Chemistry. So it's kind of like the metric system, specifically for chemistry. So as we go through and we name these things, these prefixes tend to come up quite a bit. So if we use these prefixes, these are things that, yes, you'll have to kind of be able to recall and know. It's not something that you'll be given on any sheet or anything like that. So when we have 1 stands for mono, 2 is di, 3 is tri, 4 is tetra. Now, once we get past those first 4, and even 3 really is pretty common, but the other ones really start to take on different shapes that you should be familiar with, like a pentagram or hexagram, heptagram, octagram, or a pentagon, hexagon, heptagon, octagon, nonagon. And then when I get to 10 and I see deca, I normally think of decade, representing 10 years. So mono being 1, 2 being di, 3 being tri, 4 as tetra, and then 5 as penta, 6 hexa, and so on. So those prefixes are ones that you're going to have to just kind of get straight in your head. You'll probably have to look back, and I would definitely write them down somewhere so you have them to refer back to them. So these prefixes are placed before the element's name to show how many atoms of that element is present in the compound. So note, when there's only 1 atom of the first element, the prefix mono can be left out. That's kind of an extra rule when we go through and we're naming these things. So these prefixes, they're placed before each element to say how many atoms we have. But as a note on this, is something extra to take away. It's basically one of the few rules with molecular compounds. When there's only 1 atom of just the first element, then we can leave out the term mono. So let's take a look and see kind of what these can look like. Here are some examples. So we have carbon. Okay, there's a single carbon. Notice that the mono is left out. And then there's 2 oxygens. That's the reason why we see that di prefix that's here. Or if we have a single carbon, again, the mono is left out. But then the oxygen needs mono because it's the second element. So we see mono there. Or if we have something larger, we see that we have 3 sulfurs. That's the reason why it says tri. And if we have 6 nitrogens, that's the reason why it says hexa. Also notice on all 3 of these, as an added kind of finishing to this, notice that they all end in IDE. And so we just change the ending to show that it's part of a molecular compound. Okay, so trisulfur hexanitride will be our last one. So I got a couple of examples here. Write the names of formulas for each molecular compound. So take a second, use the chart that was on that last page, see if you can come up with either the name or the symbol for each one, just to see how you do. So pause the video, try it, and come back when you're ready. Alright, so for our first one, C4H10, 4 represents tetra, so that means I have tetra, and then I'm going to say the name of the element I have, so tetracarbon. And H10, 10 is deca, and instead of saying hydrogen, we're just going to say hydride. Change that ending to IDE. In my next one, I've got tetraphosphorus trichloride. So tetra just stands for 4, so that means I have 4 phosphorus, and chloride I have 3, given that I have tri as the namelets there. After that, I've got dinitrogen monoxide. So nitrogen, the di prefix, so nitrogen has 2. Monoxide is oxygen, and mono just stands that there's 1, so a single oxygen, N2O would be my compound. And then I have CCl4, so I've got carbon. There's no mono in the front because we don't put mono for the first one if it's there. And then chloride, well, I would need that tetra to be there. And then I'd have chloride to finish off. Notice the IDE ending showing up again. So hopefully that gives you an idea how molecular compounds work. There is a little bit more, but for Science 10, really that's what we need to know for now. And so hopefully that's helpful, just kind of moving on to the next section.